Okay, so as we said, it is very important to find the eigenvalue. So here I want to also mention one thing is about matrix diagonalization. People always mention this, but it can be confusing. Matrix diagonalization is that you represent the matrix in a basis so that it is diagonalized. Okay? And that is in order to diagonalize it, you actually need to find its eigenvalues. So let me just show you the flow. Let's do this step by step. Then you will see what I mean. Right? So if I have a matrix that is A, right, I can write it as A 0, 0, A 0, 1, all the way to A 0, n minus 1. Is this okay, what I'm writing? Always row, then column. That is just the convention. You need to follow it unless you make it very clear, right? So what do we call this element? A1, 0, A1, 1, all the way to A1, n minus 1. Okay? Then I go down, I will go to A, n minus 1, 0, A, n minus 1, 1, all the way to what? A what? N minus 1, n minus 1, right? Because I have how many columns and how many rows do I have here? N column and row. So this is corresponding to what dimension we are talking about, N dimension. Very good. This is ND, right? N-dimensional matrix. Now, I can also write it as this. I hope you will be familiar with this. Just a notation. Basically, it's just saying that I have a matrix. Each element, I call it Aij. I is the ith row, J is the jth column. Okay? And of course, from here, I don't know how many dimensions. I assume I know, right? Okay? So what did we just say about the eigenvalue and eigenvector? We say this A applied to some vector and assume it is the eigenvector is going to give me an eigenvalue times the eigenvector, right? We talked about this confusing notation last time, but now just trust me. Basically, what we're saying that is eigenvalue and eigenvector. So this is lambda I, right? So how many eigenvalue does it have? Do you know? It can be repeated, or how many eigenvector it has for n-dimensional? It should have n of them, okay? So I will run from 0 to n minus 1. We have n eigenvector. And we should also have n eigenvalues, although they may be the same, some of them. Okay, we have n eigenvectors, right? So this is important, right? Now, if lambda I is a vector, how do I represent it? I actually can represent lambda I in a column form as alpha 0, alpha 1, all the way to alpha n minus 1. Right? Now, it may feel confusing, but just go back to here. Here, do you see this? This is the A. This is eigenvector. It has alpha 0 and alpha 1, where alpha 0 is 1, alpha 1 is 0. Okay? Now, we're talking about n dimension, right? I'm trying to generalize it, but maybe for simple quantum computing, we only need 2 dimensions, but you have n dimensional vector. Okay? Make sense? Is this clear? Right? You should know this is a vector, and alpha 0 to n alpha 1 are just what? Are they number, vector, or matrix? I mean alpha. Alpha 0 to alpha n minus 1. What are these? Yes, they are complex number. They are scalar, okay? We're filling up with some number here, right? The whole thing is a vector. So let's do the matrix form, right? So this one, when I say A times lambda I, actually my notation is not that good, but that's okay. A0, 0, A0, 1, all the way A0, n minus 1, A1, 0, A1, 1, all the way to A1, n minus 1, right? Practice this because you don't want this to confuse you. You need to be very familiar with this. An minus 1, 1, all the way to an minus 1, n minus 1, times alpha 0, alpha 1, all the way to alpha n minus 1 equals to, I just call this lambda. Actually, I don't want to call this lambda I. I just call this lambda. Otherwise, because this I can confuse. I just lambda, one of them, okay, one of them. Times what? Alpha 0, alpha 1, all the way to alpha n minus 1. Is that okay? Right, so basically, I just do the substitution, right? So if you feel this is difficult to understand, now we plug in all this. It's very clear. Each of them is a number. Lambda is a number. This is a number, right? But the whole thing is a matrix vector, right? This one, I can rewrite it as this, actually. I can call this is lambda 0, lambda 0, 0, 0, lambda alpha 0, alpha 1, all the way to alpha n minus 1. This is a diagonal matrix. Right? If you don't agree, try to do multiplication. What is the result of this number times this matrix? It's just lambda alpha 0, lambda alpha 1, lambda alpha n minus 1, right? What is the result of this matrix times this vector? Lambda alpha 0 plus 0 times the rest. 0 times lambda 0, 0 times alpha 0 plus lambda times alpha 1 plus 0 times the rest, right? So you see that this diagonal matrix, once you do the multiplication, you get the same as this one, right? Is this clear? I know all of you know this well, right? But we cannot make any mistake. Just let me know if this is clear. This is very important, right? If you get lost, then you cannot understand the rest of this class. Any question about why this is equal to this? Again, this is a number. Then you get lambda alpha 0 all the way to lambda alpha n minus 1. Is this okay? And this one, you do a matrix multiplication, you still get lambda times alpha 0, lambda times alpha 1, because you're doing this row times this column, lambda times alpha 0 plus 0 times alpha 1 plus 0 times alpha n minus 1. That's why you get lambda alpha 0 as the first term. No, eigenvalue is still eigenvalue, but I'm trying to show this number times this guy is just equal to this matrix times this guy. But eigenvalue is still lambda. It's not this matrix being the eigenvalue. Good question. Yeah. Okay. The reason I want to do this is that this is nothing but a little bit difficult to equal to lambda times I times alpha 0 all the way to alpha n minus 1. Do you understand what I'm talking about here? What is I? Yes. I is the identity matrix, right? Identity is 1, 1, 1, 1, 1 here, right? It's just the same as lambda times identity matrix. So actually, I did not do anything special. Many of you may already find that. Yeah, of course, lambda times identity matrix times this guy is still this guy, is still the vector, right? So I can insert identity matrix anywhere. 5 times 6 is always equal to 5 times 1 times 6. You can insert 1 anywhere. Right here, I do the same thing, right? Lambda times I. So I even don't need to show you this, but here just to show what you see here, right? So now I have this a matrix times this one equals to a matrix times this one, right? Matrix times a vector equal to the matrix, another matrix times a vector. All right? I can move it to this side. Then I have A minus lambda I times lambda I equal to 0. Right? Because this is A. Right? Times lambda. No, I don't want to do I. Right? I just do lambda. Right? This is A. A times lambda. Right? This is the vector. Equals to lambda I times lambda vector. I can move this one to the left, right? This one, I move to the left. Then it becomes subtraction. I can factorize it because matrix, right, on the vector. Is that clear? Yeah.
Is that the reason why you didn't use the I subscript in this equation?
I can use it, but since if I put I, then this alpha, I better put I also because I did not put I, so I try to make it general. It doesn't matter. Yeah. No special. It's just a variable.
Okay, so there was a lambda I and alpha 0.
I don't need to do that, but then it becomes looks like it's better I put I, right? Because for different lambda I should have different alpha 0, right? That's why I just put lambda. Yeah. Good, right? Now, I want you, as I said, our class is like, we don't have tutorial. Make this like a tutorial, right? In other school, they have PhD students. You have 1 hour tutorial every week, and then you can wait to ask those subtle questions. Let's understand now. Don't go back to read the book if you don't have time. You should read the book, however. Okay, if this is clear, then the point, this is, what does it mean? Right? So this I'm not going to prove it to you, right? In order to have this is you learn in other class, to have long trivial solution. It means that in order to satisfy this equation, if lambda is 0, everything is 0, it's satisfied, right? Lambda is 0, 0, alpha 0 equal alpha 1, etc., right? Then you satisfy, correct? That is a trivial solution. But we know that that is not it, then I cannot find my eigenvalue, my eigenvector. My eigenvector is not 0. 0 is a trivial solution, right? In order to have non-trivial solution, then we need the determinant of this matrix equals to 0. Determinant. Right? If you forgot what it is, you can Google later, but it is very easy for a 2D case. I will show you, right? But what I'm trying to say is that in order to find the eigenvalue of the matrix, I showed you one time already. Remember how you did that in sigma x? And it's also in the assignment. You just assume it is AB, the eigenvector is AB, right? The eigenvalue is C, then you equate the equation, right? This is also the same. They are equivalent. But here I would like you to just use this equation instead. Then you can find the eigenvalue directly instead of eigenvector first. Okay? So with this, I come up with this equation. You actually don't need to know how to derive this. But if you want to continue on linear algebra or quantum computing, it's better to understand exactly what it is doing. Right? You don't need to able to do it, but you need to understand what people are doing. Now, then this is the theory. Then, when I write down this A in this way, I'm using a certain basis, right? As I said, I always need to express in a basis. If I express it in the basis by its eigenvector, then the matrix is going to be diagonal. That's what I try to say. Now, I have A Now you might not be happy. I keep changing the symbol. Now I call it I. Okay, but you should be very, you should not be confused with that. Okay, I means the ith eigenvector. Lambda I means the ith eigenvalue. You could put I also. I just want to put under I. Okay, I have this liberty to do that, right? What is I? If I represent its eigenvector in its basis instead of I, what is 0? It means what is the first basis of, what is the first eigenvector of A when I represent it in the basis formed by its eigenvector? Yeah, very good. I thought my sentence is very confusing. I'm asking is, what is the representation of the first eigenvector of A? The first eigenvector of A, or the zeroth, let's say zeroth, right? The zeroth eigenvector of A, when it is represented in the basis formed by its eigenvector, right? I'm trying to ask you, what is the first character in English when you write English with English alphabet? What is that? A, right? The first character in English when you write it in English alphabet is A, right? I can use Japanese to write English character also, I believe so. They have Japanese, hiragana, katakana, I don't know all them. You can write in that letter, I say that is corresponding to English A, right? But now if I write it in Japanese character basis, the first character of English, which is A, will have a special writing, R or whatever. But now I'm asking, what is the first eigenvector of A when I write it in the basis formed by the eigenvector of A? Right? So you're right. Right? I keep repeating the same thing. It must be this. Because this one is telling me I have one component of the first basis. Vector. Correct? That is exactly what it means. Is it clear? So when I represent the matrix in the basis formed by its eigenvector, its eigenvector must be in this form also, right? Then what is the ith eigenvector? How do I represent it? It must be 0, 0, and then 1, and then 0. And this is the ith location, right? And the last one, n minus 1, it must be 0 all the way to 1. This because this is the definition. Right? I hope you understand the representation of basis, right? I think I gave a pretty good analogy on English, right? Or in Greek, right? If I can say that, what is the first character of English alphabet? Alphabet is the basis of English, right? The first character in English represent in Greek. Then you may say alpha, right? Or something, right? But in English basis is A. Okay. So that is what all I want you to see, right? So as a result, A must be equals to lambda 0, lambda 1, lambda n minus 1. And this means everywhere is 0. If I write the matrix A in the basis formed by its eigenvector, then it is diagonalized. Now, I will go to show, I did not prove it, I tell you, but I will show you it is right. So you see that when people say, I want to diagonalize the matrix, it's equivalent to find the eigenvalues. Because if you find the eigenvalues, you just put them in the diagonal. You diagonalize the matrix already. Okay? And each of the bases correspond to the eigenvalue you put here. Now let's check if what I'm saying is correct, right? Let's just check arbitrarily. What if the A is applied to the jth basis, jth eigenvector of A, right? A applied to the jth eigenvector of A. What does it look like? Is lambda 0, lambda 1, lambda j, lambda n minus 1? This is A, right? Diagonal. And you multiply by what? Lambda j, how do you write lambda j? I mean, how do you write j vector, the j vector in this basis? 0 all the way to 1, and then all the way 0, right? And this 1 is at the jth location. Now you do a multiplication. This row multiply this one. Everywhere is 0, except this is lambda 0, but this is 0 here. And when it is 1, this is 0 here. So you must get something like this. 0. Still 0. Until what? Until this jth row, you have all 0 before the lambda j, but then you have lambda j times 1, and then 0 times 0. So here you get lambda j. And then the rest are still 0, right? So this is equal to what? This is equal to lambda j times everything, 1, and then 0, which is just lambda j times j, right? So in the matrix times the vector E2 is eigenvalue times the eigenvector. So indeed, for each of them, this matrix is still behave correctly, right? So just to check that, to show you that this is the case. Now, why this is important? Because you will always see diagonalization in quantum mechanics. This is very important. It makes your life much easier in the math. Okay, so matrix diagonalization is equivalent to finding the eigenvalue. If I don't know the eigenvalue, I cannot diagonalize it. If I can diagonalize it, I can find the eigenvalue. And again, what is diagonalizing it? It means making it into diagonal by finding a basis, so it is diagonal. But this basis happens to the basis formed by its eigenvectors. Okay? Any questions?
So
Yeah.
I guess the principal application of calculating eigenvector is to be able to diagonalize it with the NW at true state. So we're learning.
Yeah.
This seems to me like it's easy for them for that. Because we're able to
You can say that. But another reason to do that is because we want to either find eigenvalue because it corresponds to the measurement that you can get. Yeah. Now, I know a lot of theory and very daunting, but the good thing in quantum computing is we are 2D. Let's just look at example, right? We just keep practicing, right? Difficult thing becomes easy if you keep practicing, and don't be afraid of that. Let's look at an example. We did that already, and that is in the assignment. Sigma x equals to 0, 1, 1, 0. This is a matrix A. This is the matrix A, right? We want to we already learned how to find the eigenvalue, eigenvector. Remember? We set sigma x. That is another part of the assignment, right? We say, oh, let's do this, sigma x times AB equal to C times AB, right? This is just like method 1. Right? And then you equate the equation, you get ABC, you get the eigenvector and eigenvalue. Okay? Now I'm going to use what we have learned. I say that I know that the eigenvalue can be found by using this equation also. Yeah. Okay? So let's look at the determinant, see what it is, right? Sigma x is what? It is 0, 1, 1, 0, and then you say minus lambda, lambda, 0, 0, determinant, right? Which is just equal to negative lambda 0, 1, negative lambda. Is this okay? I do matrix addition, subtraction, right? 0 minus lambda, 1 minus 0, 1 minus 0, 0 minus lambda. I get this one. And then I say, well, I want to find determinant, so I just put the determinant symbol. For 2D, it's very easy. Multiply these two elements diagonally, and then subtract the multiplication of these two. That is the determinant. If you forgot, memorize this. This equals to negative lambda times negative lambda minus 1 times 1, which is equal to lambda squared minus 1, and we say this is 0. Is this okay? Right? For other higher dimensional determinants, you cannot do this. Up to 3-dimensional, still okay. 4-dimensional, you need to follow the rules, right? For 2-dimensional, it's easy. This one, what do you call? West-north to southeast corner multiplication minus southwest to the northwest multiplication. That is the determinant, right? You get this. So what is lambda based on this? Yeah. Is this the same as what we learned earlier? It's the same, right? So that is just another way, equivalent way. This is method 2. Okay, I'm a little bit lost also. Look, so this is the method 2 to find it, but then how about the eigenvector? How do you find the eigenvector? Now you have no choice, you need to go back to the equation. Okay, so we then try to find the eigenvector. Right? So you start with this one, sigma x times AB equals to lambda 0, the first eigenvalue, right? It's up to you to choose which one. We can start with lambda 0 equal to 1, right? Then you have sigma x 0, 1, 1, 0 times AB equals to 1 times AB, right? And then on the left is just matrix multiplication. I hope that you are familiar with this. This is what? 0 times A plus 1 times B, right? Which is B. And then 1 times A plus 0 times B, right? Which is A, right? Equals to AB. So what equation do we get from here? No, equate the row, right? What do we get? First row, first element, B equal to A. Second element, A equal to B, right? So it means it can be anything. But however, in quantum computing, what do we say? It needs to be normalized. That is the first thing, right? So there are many things we can choose. So I know that you need to be normalized. It means A squared plus B squared must be equal to 1. But now you say A equal to B, right? So it means 2A squared must be equal to 1 because A equal to B. Then it means A equals to plus minus 1 over 2. Okay? I just choose one of them. It doesn't matter, right? So I'm going to choose plus. Okay? So I choose plus. Then the first eigenvector V0 equals to 1 over square root 2, 1, 1. Okay, because this means that A equal to 1 over square root 2, B equal to 1 over square root 2. And if you ask yourself what it means, actually, this V0, it also means square root 2. Don't want to put in the matrix form. What basis are we using here? What basis when I write it 1, 1, right? Or when I write the matrix as 0, 1, 1, 0, what basis are we using? The Z eigenvector basis, spin up, spin down. Yes. So this one means it is one component of 0 plus one component of 1. Right? And we call this one the plus state, which is the eigenstate of the sigma x matrix. But it has the same eigenvalue as the 0, right, in the sigma c. Now think about it, this is a very subtle but very important concept, right? I keep talking about this basis. If not clear, think about it or talk to me. Yeah. I don't want to put broad sphere. One is I have not teach you yet. Another is can be even more confusing because you will think that in 3D space. Okay, let's just think about what I showed you earlier. I mean, just know that it is different bases. Yeah, different eigenvector from the different bases, right? Plus and minus. The point is when we write this, we are using the sigma c eigenvector basis. Okay, any questions? Now, of course, you can do the same thing, right? You try it yourself. You can try. Now, try to find the eigenvector corresponding to lambda equal to -1, lambda 1. And you will find that it is the minus, which is 0 minus 1. Okay, I will come back to here a little bit later, right? Let you copy, finish this one. So I said I'm writing it in the basis formed by sigma c. Why I know that? Because I already have this one. This is writing in the basis formed by sigma c. Sigma c eigenvectors. Okay, so everything else will be that, right? Now what if I write it in the basis formed by its own eigenvector? What can it be? We just discussed. Sigma is like A, right? So I'm writing sigma in the basis formed by its eigenvector, right? Just now, it's just like I'm writing the English, a textbook in English, in the basis formed by Japanese, for example. Now I want to write the same book, same content, in the basis formed by English. What will it look like? We just discussed. When you form in the basis formed by its own eigenvector, how will it look like, the matrix? This is what I just said. How will it look like? When I write the matrix in the basis formed by its eigenvector, how will it look like? It will be diagonalized, right? And what are the diagonal elements? Will be the eigenvalues. So based on this, right? What should this look like? Can you guess what is the matrix of sigma x? One, zero, zero minus one. Why? Because we just find out the eigenvalue is plus minus one, right? Then it must be plus minus one. Okay? Because I want to put the eigenvector correspond to eigenvalue 1 as the first vector, so 1 is here. Have you seen this before? This is sigma c, right? But this is sigma c when sigma c is written in the basis formed by sigma c eigenvector. When we write sigma c, up to now we keep doing sigma c basis. We can call it computational basis. That is what people usually say. I should mention that. We have been using a computation way, maybe English. We keep talking to each other in English. That is our computational basis, right? So when the sigma c is written in the basis formed by sigma c's eigenvector, it is 1, 0, 0, 1, 0, 0, negative 1. Now, if I write sigma x in the basis formed by the eigenvector of sigma x, is also 1, 0, 0, 1. They are not equal to each other. Think about that. This one is when I write it in sigma x, I just call it sigma x basis. When I write in sigma x basis, the form looks like when I write it in, like sigma c, write in sigma c basis. Okay? But they are not equal to each other, right? Because we are in different bases. But does this make sense, actually? You think about that. Now, let's go back to, I did not talk about too much physics, but we know this sigma x, sigma c is related to the, let's say in the spin case, related to the magnetic field, right? When the magnetic field is pointing upward, then the corresponding operation is represented as sigma x, sigma c. When the magnetic field is pointing in the x direction, the corresponding operation is represented by sigma x. Now, in the universe, you don't have gravitational force, right? We discussed this earlier. It's isotropic. Z, x, and y is the same, right? The physics should be the same. So if I put the magnetic field in the z direction and study the property of the electron, we are not saying the electron is spinning up. We're just saying that what are the possible value of the electron in relationship to the magnetic field. It must be going along or going against the magnetic field. So I have a certain matrix. Now you put in the x direction, its property is still the same, going along and going against the magnetic field. So we should have exactly the same physics. So there should be no difference why you prefer z, just because you're taller than me. And I'm fatter, that's why I prefer x, you prefer z. No, right? Now this revealed the fact. If you represent sigma c in the sigma c eigenbasis, you should be the same as sigma x represented in sigma x eigenvector basis. And that is the same in other direction. And now go back to the homework. I ask you, what if it's in arbitrary direction? What do you think? At least for the eigenvalue, I give you the answer now. They should be the same, right? Because maybe since I'm born, my parents trained me to look horizontally by 90 degrees. All the physics should still be the same. It should not change just because my parents preferred me to rotate 90 degrees to read. Yeah. When it is represented in sigma c basis. Yeah. Yeah. That is what was not clear at that time. Correct. Can you guess if I don't mention? It must be in the same basis. Source of sigma c basis. No, no, no. Sigma y is still in what we wrote, what you just said, right? 0, negative I 0. This is in sigma c basis. Okay? But if you write in sigma y basis, what would you be? What would it be? Can you guess? Yes. Then it becomes 1, 0, 0, negative 1 in the sigma y basis. Again, that should be the case, right? Do you see what I mean? Well, very good question, right? So yes, you can say that if they are represented in their own eigenvector basis, they should be equal to sigma c in sigma c basis, because sigma c in sigma c basis means sigma c in its own eigenvector basis, right? Statement is exactly the same. So very good, right? So here I just want to remind you, this is just lambda 0, 0, lambda 1, as what we learned earlier. Okay? And because of this, what is the first basis vector in this case? When I write in the sigma x basis, what is the first basis vector? Still 1, 0, right? But this time, this is not 0, this is plus. Yeah, you see it is 1, 0, but this is the sigma x basis. Okay? And then the second basis vector is going to be 0, 1. And this is minus. Contrast what we learned earlier for sigma c. Right? In the sigma c basis, no. Right? The first vector is also 1, 0, of course. But you're in the sigma c basis, what is this? 0. The second basis also have exactly the same form. Right? And now when it is confusing, we need to say clearly which basis we are talking about. 1. Okay, and now we go back to the fake figures that I've shown you earlier, the fake one. We try to hijack the two-dimensional one. This basically saying what it is saying here. Right? Of course, this is fake, but basically it's saying that if I represent sigma x in this plus minus basis, the form is the same as I represent sigma z in this 0, 1 basis. Okay? Think about it. And any questions? Yeah, this needs a lot of thinking. I can tell you the most confusing part when I learn quantum computing or quantum mechanics is this part. The transformation of basis. You need to be very good at this. At least you need to be aware of this, yes. Zero and 1 is the name we give to the eigenvector of sigma c. Plus minus is the name we give to the eigenvector of sigma x. So if you don't like this, you can say the first basis vector in sigma x basis. Yeah, but the convention is plus minus. So that is a very good question. Again, anything inside this Dirac bracket, that's why I argue with you so much time, is just a name. That's why I never feel that I'm wrong, because I have the freedom to choose anything. The only thing maybe I make it confusing, right? So that is a good question. This is just a name. I put it 0 and 1. You can put in whatever French, Hindi, Chinese, Japanese, no problem, as long as it is clear. Okay, these are just names, right? So that's why sometimes we do spin up and spin down. This use left and right, right? We do that, right? We will see literature, sometimes they will give you this. In your heart, you should tell you this is the first or second basis of the basis, yeah. First or second basis vector. Yeah.
So moving up to that first thing you're writing there on the top left, sigma x equals 1 to 0, 0 minus 1, and 1 and minus 1 as the eigenvalue. Why did you start with 1 on the top?
I just want to follow the convention.
But if it was minus 1, if we use minus 1 first, then does that make things wrong?
You won't make it wrong, then you should know that it's eigenvalue. The first vector is corresponding to eigenvalue negative 1. Then in all your computation, you don't have this figure. It's just the convention. We correspond the 1 to the 0 state. Right? It doesn't matter how you write it, but you better follow this, otherwise you're going to mess up many things.